Okay, in this video we're going to have a look at velocity time graphs or speed time graphs. It's a little bit different from we've previously looked at distance time graphs, and these are essentially concerned with acceleration. These show us the acceleration of an object. So let's have a look, let's get into it. Alright, so first things first, let's have a look at an example of a speed time graph. So you'll notice here the key difference, and this is the first thing, whenever you get a graph like this, the first thing you should be looking out for is what's on the left hand side here. So in this case we've got speed rather than distance. And what that means is, you could imagine, for instance here, the speed might be 50 kilometers per hour, right? So I might be cruising at 50 kilometers an hour in my car. But what that means is a flat line here, if we've got a flat line like this along the top, well, it means the speed isn't changing. So on a distance time graph, it meant the distance wasn't changing, which means we're still or we're stationary. But here, if the speed isn't changing, it actually means we have a constant speed. So if I'm ticking along here, well, as time carries on, my speed is staying at 50 kilometers per hour. So on a speed time graph, a flat line means a constant speed. A line that's on an angle or a line that's sort of sloped upwards is actually accelerating. You can see, for instance, this line here was maybe me in my car when I first started. I was going 0 kilometers per hour at the beginning, and I started to accelerate or speed up. So at this point I would have been doing maybe 25, and after a certain amount of time I would have reached here 50 kilometers an hour, and then I was going at a constant speed. So on a speed time graph, a straight line actually means acceleration. So your distance time graph, you remember, a flat line was a stationary object, and a sloped line was a constant speed, and a curved line was acceleration. Well, now because we've got speed on the side, we kind of skip that first step. A flat line is actually a constant speed, and a sloped line like this is actually an acceleration. And it pays to just try to think it through logically. Think of what have I got on the side here. So if this is 50 kilometers an hour, well, a flat line here means I'm staying at 50 kilometers an hour, constant speed. And acceleration, well, here as I go up, if I've got speed on the side, it means my speed is changing. If my speed is changing, it must be accelerating. Now, a line that slopes downward, like this over here, actually tells us that the speed is changing as well, but the speed is getting less. So if my speed is getting less, we're decelerating. Now, one thing just to be aware of here is we can refer to this as deceleration, or we can even actually refer to it as a negative acceleration. So we could work out a value for acceleration, and it'll be negative because it's going down rather than sloping up. The other thing is, just before we move on, is that we can actually still work out the distance that's been traveled by working out the area underneath the graph. So in this first section here, so we could call this section A, in this first section here, if we wanted to know how far we had gone in that time, we could work out the area underneath the graph. And that needs to, you just need a little bit of knowledge of maths here. To work out the area of a triangle, like this one, to work out the area underneath here, we would take half the base times the height. Now the reason for that is if we take the base times the height, we'd actually be working out the area of this square here. And you can see the red line through the middle. We actually only need half that area for the triangle. So the area for a triangle is half base times height. And you don't necessarily need to memorize this formula if you think you can remember kind of looking at this well to work out the area underneath here. Alright, in this grey part here. Alright, to work out the area underneath here, you can see it'll be the base times the height, but we only actually need half of it because it's a triangle. If we wanted to work out the distance that was covered during this part of the graph in here, alright, well, we would just take the base times the height would be the area underneath this part of the graph. So the area underneath a distance time graph tells you the area underneath the speed time graph tells you the distance that's actually been covered. So let's have a look at a few questions, and I've got a couple that are sort of nice and tricky, some past exam questions. But before we do that, we're just going to link it back to the triangle like we did with our distance time graph. So in this case, if we look at my slope here, so remember, so acceleration, we can use our triangle here, is equal to a change in velocity over, and it's often actually a change in time. Now you won't lose any marks if you leave off the triangles, but it's good to remember this is the change in velocity. Alright, and if we look at this example here, well, let's have a look. What's the slope of the graph here? So remember, a slope of a graph, or the gradient, so another word for the slope is the gradient, is the rise, or the y-axis, over the run. So rise, how much we go up for every bit that we go across. So here we've got the rise. So if we're working out this section at the beginning here, we've got the rise is speed. So the rise is a change in velocity. We went from 0, a velocity of 0 here, maybe up to, maybe at this point we're doing 40 meters per second. So that's a change in velocity as we go up, over our run is a change in time. So the slope of the graph, if it's a velocity, the rise, over the time, the run, velocity over time, is acceleration. So the slope of our graph tells us the acceleration. And what that means is if I've got a steeper line like this, it means it's accelerating, it's speeding up more quickly than this one here. A flatter line, like one across like that, it means it's accelerating, but it's speeding up at a much slower rate. Okay, let's have a look at a couple of questions. Oh, jumping the gun a little bit there. Alright, so I'll just zoom out a little bit, and I will read it in case it's a little bit too small for you. Alright, maybe we can fit those together on the screen there. Okay, great. So on Athletics Day, so this first one here, on Athletics Day, two friends compete in the same 100-meter race. The speed time graphs for 12 seconds of the race are shown below. From the graph, who has the greater acceleration in the first 2 seconds? Give a reason for your answer. No calculation is required. So who has a greater acceleration here? Well, the answer is Sam. So we've got two options here. We've got this line here, which is Sam, and we've got this dashed line. I'll do that and highlight that in a different color. We've got this dashed line here, which is Tamara. So Sam has a greater acceleration because, and it's exactly what we were going through a second ago, the slope or the gradient of the graph tells us the acceleration. Sam has a steeper slope or gradient, which means the acceleration is greater. And we could explain that even more fully if we wanted to. We could say that the slope is equal to the rise over run, which is equal to velocity over time, and that's basically acceleration. So Sam has a greater acceleration than Tamara. It's a steeper line. And that's really all they want there, no calculation required. Now here's where we get into some calculations over here. Use the information in the graph to compare the speed and acceleration of Sam and Tamara in the first 10 seconds. So the first 10 seconds takes us to, this point here. Alright, so we've got 10 seconds is here. So we need to compare what happens before that point. So Sam's speed and acceleration. Well, let's have a look. Sam is the one I've highlighted in yellow here. So first off, what's his maximum speed for the there's maximum speed in those 10 seconds. So Sam reaches a top speed here of 9 meters per second over here. So his top speed, or velocity, is 9 meters per second. Now let's talk about the acceleration. So we've got the speed. Let's talk about the acceleration, what's happening during that bit. So this the slope up bit here. So we can work out the acceleration is equal to the change in velocity over our change in time. And I'll be lazy, just put a t there. So the change in velocity has gone from 0, so it's easy. We start at 0 up to 9. So the change in velocity is 9. And we could do it properly and go 9 minus 0, but it's going to be 9. 9 divided by, now how long did that take? It was 2 seconds. Alright, so that means he accelerates at 4.5 meters per second is his acceleration. So now we should put that into a sentence, and if we fully want to describe it, we should actually say that Sam accelerates, he's speeding up, he accelerates at 4.5 meters per second, that lasts for 2 seconds. So he accelerates at 4.5 meters per second for 2 seconds, and reaches a top speed of 9 meters per second. It's the flat bit here. He's going at 9 meters per second. So let's now have a look at Tamara, alright, the dashed line here, and try and work that one out. So let's start with the acceleration here. So we could say her acceleration, okay, we take our rise, so she's gone from 0 to 10 meters per second. So acceleration equals a change in velocity over time. So in this case, the change in velocity is 10. We could go 10 minus 0, but the change in velocity is 10 meters per second divided by, now it's taken her, alright, to reach that speed, or to that acceleration is over 5 seconds. So we can say her acceleration is only, right, 2 meters per second. But she accelerates at this rate she's accelerating at 2 meters per second for 5 seconds. Oh, I'm going to get cut off there, so just write it for 5 seconds. So up here, he was accelerating at 4.5 meters per second for, it was only 2 seconds. And so Tamara here actually reaches a top speed of this flat line bit here at 10. After 10 seconds, she's going 10 meters per second. So her top speed here is 10 meters per second, and I've just read that straight off the graph. So be careful when your values for acceleration are always meters per second, and values for speed or velocity are always just meters per second. So if we have a look at this, essentially Sam accelerates for 4.5 meters per second. We worked out the acceleration from the slope of the graph here, and he accelerates for 2 seconds, reaching a top speed of, he then levels off at 9 meters per second. Tamara accelerates, the slope of her graph during this first part is 2 meters per second. So it's not as fast an acceleration, she's not speeding up as quickly, but she accelerates for 5 seconds. So she reaches a speed of 10, a max speed up the top here of 10 meters per second. So in terms of the comparison here, it's literally just kind of putting this into words. We basically say that Sam has a greater acceleration, so his rate of acceleration is faster for the first 2 seconds, but he doesn't accelerate as long as Tamara. So she actually reaches a faster top speed in the end. She reaches a faster constant speed in the end. Now it's also worth noting there was actually also a mark in there for saying that between 5 and 10 seconds neither of them were actually accelerating anymore. Alright, great. So we've got one more question to go. I'm not going to write that all out, but comparing it here, it's basically saying Sam accelerated more quickly, but only for 2 seconds. Tamara accelerated a little bit more slowly, but for 5 seconds. But because she was accelerating or speeding up for a longer period, she actually reached a faster top speed. We could also add in that fact that during between 5 and 10 seconds, neither of them were actually speeding up. So we've got one last question to go, and this is a pretty good question. All right, a little bit tricky. Oh, sorry, there we go. Here we go. All right, so we've got our graph here again, and I'm sorry if it's a little bit small. I'll read it out for you. So it's the same graph as before. Use the information in the graph and any necessary calculations to show which runner, Sam or Tamara, finished at 12 seconds. So at the end here at 12 seconds, which one of them actually finished the race? I'll zoom in on the graph a little bit now. So the graph is simply repeated here. Right, so the graph was on page 5 of this exam. The graph is repeated here so we can work this out. Now what you need to notice is at the start it told us the race is 100 meters. So that's something that you might be thinking, how can we work this out? So what we want to know is which one of these two runners has covered a distance of 100 meters or more when we reach 12 seconds. So this is a little bit, tricky, but what we've got to do is work out the area, the total area under each graph. The total area under each graph. So for Sam, so the distance he's traveled after 12 seconds is the total area under his graph. So for Sam, we do that by taking, so the area, we split it into sections. We work out the area under this triangle part here, under this triangle section here. I'll try and shade that in. Okay, so that is the distance Sam's travelled. Sam's distance is going to be, so we can string this all together, it's going to be 1/2 times the base, so that's times 2, times the height, which is 9. So we've worked out that's the bit in yellow here. Next we've got to work out the area under this big block section. So we're going to work out the area here under this part of his graph. Okay, I'm not going to spend, it's going to take me too long to colour all that in, so I'll just put some, so we've got to work out the area underneath here. Alright, so for this it's just going to be the length times the height. So for this case, we're going to we're going to add the length times the height. So from 2 to 10 here is going to be 8 times the height up here, 8 times 9. Okay, and lastly, we're going to have to work out this last section here under the graph. Now to do that, it's actually easiest if we split it into this block here. So if we split it into this block here, and this little triangle up here. So to work out the total area, it's just easier if we split it into these sections and then add those all together. So to work out this this pink block here, we take the base, so it's 2 across. So it's 2 times, and the height again is 9. And then our little blue triangle here, so across is 2, now it's half because it's a triangle, half the base times the height, so half times 2 times, and the height there is it's just 1, we're only going up by 1. Alright, so if we add that all together, you'll find it actually equals 100 meters. So we already know the answer now. Sam is the one, so we could say here, therefore Sam has finished the race. And you'd need to say that as a sentence to get, your full marks. You'd have to note there, you'd have to say that Sam is the one who's finished the race, obviously first. Now let's have a look. We should work out Tamara just to be sure. Maybe it's a trick question and they've both finished the race. So I'll clear that, and if we do Tamara, if we work out the area under her graph. So the area, we'll start by splitting it into these sections again. So the area underneath this block here, right, this blue kind of triangle here, the area under here. So Tamara's distance, Tama, it's not Tamara, it's Tama. Tama's distance he's travelled is going to be, so the area of this triangle, so that's going to be half times base, which is 5 across, in this case 5 across here, times 10. Plus, now we work out the area of, so again we're splitting it into sections, we can work out the area of this block here. So the area of a block, remember we don't halve it, so the area of the block here is, we're going 5 across and up 10, so 5 times 10. Sorry, that's just my bracket, if that wasn't clear. Alright, plus, alright, now our next part, do this bit in pink, we've got this block here, so we work out that block there. The area of this part here, so that would be, it's 2 across, times 10, it's going 10 up there, and plus lastly we've just got to work out this little triangle bit over here. Alright, this little triangle bit here, because that's going to give us, alright, if we follow Tama's line up and along here, once we've got that, we're going to have the total area underneath his graph. So that last little triangle, the last little triangle is actually, it's going to be, sorry, it's a terrible bracket there, half times, now the base there is 2, and it's gone up by, we've gone up there by 2.5, 2.5. Okay, And if we add all of that together, if you plug it into a calculator and add all of that together, you'll find it is actually 97.5 meters. So Sam, at the end of the 12 seconds, Sam is actually the one who's done the full 100 meters, and Tama, unfortunately, at 12 seconds, he's still got another 2.5 meters to go. So he's just 2.5 meters behind Sam. Cool, well I hope you found that helpful. So you can work out from a speed-time graph, you can still work out the distance by taking the area underneath the graph, and you can work out speed, from a speed-time graph, you can work out the acceleration from the slope for a part of a graph. And those are the kind of things that they'll ask you to do. Cool, well I hope you found it helpful, and good luck for your exam.